In this video, we will conclude our study of logic and truth tables by introducing quantifiers and then working through some exercises related to quantifiers. So at the beginning of the lecture note, you'll see just sort of an open question. Consider the statements below and then try to decide which, if any, are equivalent to each other. And this is going to help us to introduce the idea of quantifiers. So the first statement is you can fool some people all of the time. And the next is you can fool everyone some of the time. You can always fool some people. Sometimes you can fool everyone. So if we think about these statements, you can always fool some people versus you can fool some people all of the time. They're not exactly the same. They sound very similar, but in the one case you have some people, a group of people that you can fool all of the time, as opposed to all of the time you can find some people to fool. So the difference is sort of subtle there. And similarly, we can think about the relationships between all of these things. But what this is leading up to is the idea of quantifying these logical expressions. So it's nice if we can use variables in our mathematical sentences. For example, suppose we want to claim that if n is a prime, then n plus 7 is not prime. This looks like a conditional statement, an if-then statement. And we might like to write something like Pn means n is a prime, and write Pn implies not Pn plus 7. But this is not quite right because we haven't specified anything about n. So at this time, it would be what we call a free variable. If we plug in a specific value for n, we do get a statement. For example, if we said 5 is a prime, then 5 plus 7 is not a prime. Then we plugged in a value for n, and we get a statement, and it turns out, in fact, that it's a true statement. In fact, if we plug in any natural number for n, we will get a true statement. So what we really want to say is that for all values of n, if n is prime, then n plus 7 is not. So it's this for all values of n, which is what we forgot to say up here. So what we needed to do is quantify the variable. Although there are many quantifiers in English, such as many, few, most, some, in mathematics we generally stick to two quantifiers, the existential quantifier and the universal quantifier. So we'll introduce those here in this purple bubble. The existential quantifier will be denoted by this symbol, and this means there exists. So existential, there exists. And you might see it used like this. We would say there exists x such that x is less than or equal to 0. On the other hand, the universal quantifier, which is denoted by this symbol, in words, that means for all or for every or every. And you might see it written like this. We would read this as for all x, x is greater than or equal to 0. As with all mathematical statements, we would like to decide whether a quantified statement is true or false. For example, consider the statement here. For all x, there exists y, y is less than or equal to x. Is this true? Well, again, we haven't stated anything about our domain of discourse. So is there any particular set from which we can take x or y? Do we mean positive integers, real numbers, or some other set? In discrete mathematics, we're often going to be using the set of natural numbers 0, 1, 2, 3, 4, etc. So let's take that to be the domain of discourse when we consider this statement. So we're thinking about x and y being two natural numbers, and we want to determine if the statement for all x, there exists y less equal to x, is true. Well, maybe we could let y be x minus 1. Then is it true that no matter which x I plug in, x minus 1 is less than or equal to x? Almost true. The only problem occurs if x is equal to 0. If x is equal to 0, then y would be negative 1. And for our purposes, negative 1 is not a number. That means negative 1 is not in the set of natural numbers, so we don't care about it. So since this quantifier says this must work for all x, we see that the statement is false. We show that the statement is false by finding one number, which was 0, for which the statement was false. So in symbols, what we found out is that there exists an x such that for all y is greater than or equal to x. That's x equals 0. X equals 0 is such an x such that all natural numbers are either greater than or equal to it. So to show that the statement was false, we proved that the negation was true. And this will often be the strategy for these types of things. So here's the information about quantifiers and negation. The negation of the universal quantifier for all x, p of x, the negation of that statement will be the existential quantifier there exists x such that not p of x. So in a sense, we pass this negation through the quantifier. As we pass it through the quantifier, we flip the quantifier from, in this case, universal to existential. And the opposite is also true. If we want to negate an existential quantifier, so we want to say the negation of there exists an x such that p of x, that will be equivalent to for all x, negation p of x. So we passed this negation through the quantifier, and we flipped the quantifier from there exists to for all. So now let's work through some exercises together. First, we're asked to write the following statements using quantifiers and symbols as necessary. The first statement is the sum of the first 100 positive integers, first 100 odd positive integers. Well, this is not a logical statement because we cannot assign a truth value to it. We can't say it's true, the sum of the first 100 odd positive integers, or it's false, the sum of the first 100 odd positive integers. The sum of the first 100 odd positive integers would just give you a number, so we can't assign a truth value to a statement like this. The next statement is everybody needs somebody sometime. So I noticed that this word everybody signals a universal quantifier. So I could let my proposition be X needs somebody sometime. then this would be for all x, P of x. How about C? Well, C is pretty straightforward. If we let the Broncos will win the Super Bowl be P, and I'll eat my hat be Q, then this is just P or Q. The Broncos will win the Super Bowl, or I'll eat my hat. D, we can have donuts for dinner, but only if it rains. Let's let it rains be P. We can have donuts for dinner be Q. Then this will be P implies Q. Or if P, then Q. Or Q only if P. And then E, every natural number greater than 1 is either prime or composite. So we could say a natural number is greater than 1 is, say, P. And let's let Q be N is prime. And let's let R be N is composite. We're talking about the domain of definition being the natural numbers. Then this would be R implies P or Q. If a natural number is greater than 1, then it is either prime or composite. And finally, F, this sentence is false. Again, this is not a logical statement. Because we cannot assign one truth value to it. Okay, example 2. Suppose P is the proposition Jack passed math and Q is the proposition Jill passed math. Translate Jack and Jill both passed math into symbols. This is simply P and Q. Translate if Jack passed math, then Jill did not into symbols. So P, if Jack passed math, then Jill did not should be not Q. C, translate P or Q into English. That should be Jack passed math or Jill passed math. Maybe we could say Jack or Jill passed math. D, translate negation of P and Q implies Q into English. So the negation of P and Q is the negation of Jack and Jill passed math. So we want an implication, so I'm going to start with if, and then the negation of Jack and Jill passed math is if both Jack and Jill did not pass math, then Jill passed math. And it's understood that when I say if both Jack and Jill did not pass math, that should mean both at the same time. So it could still be Jack passed or Jill passed. It doesn't mean that they both failed. Maybe to be a little more clear, we could say if Jack and Jill did not both pass math, so that it's clear what we mean. Finally, suppose that we know that if Jack passed math, then so did Jill. So we know P implies Q is true. What can we conclude if we know that Jill passed math? So our proposition is if Jack passed math, then Jill passed math. Knowing that Jill passed math doesn't really tell us anything. Jack still could have passed or he could have not passed. So we'll say Jack may or may not have passed. Whereas if we know that Jill did not pass math, but the statement if Jack passed math, then so did Jill tells us that for sure if Jack passed math, then Jill was going to pass. So if Jill did not pass, then we know Jack did not pass. So the difference here is that in situation 1, Jill passed. She might have passed because Jack passed, or she might have passed on her own and Jack didn't pass. Whereas if she didn't pass, we also know that Jack did not pass. Now, we're asked to translate these logical expressions, the symbolic logical expressions, into English. So the first one, I have the universal quantifier. So I know that that should be for all x or for every x. And then I have an implication inside. So I'll say if the proposition EX, then the proposition EX plus 2. We weren't told what E is, so that's the best we can do. For part B, I have my universal quantifier for all x. I have an existential quantifier. There exists y such that sine of x is equal to y. On the other hand, C says for all y, there exists x such that sine of x equals y. And these are different statements. Finally, for D, we have the universal quantifier for all x and then the universal quantifier for all y. So we'd say for all x and for all y, or we could have just put comma for all y. Inside the parentheses is an implication. So we're going to say if x cubed equals y cubed, then x equals y. Now suppose that p of x is some predicate for which the statement for all x p of x is true. Is it also the case that there exists p of x is true? Let's think about this. Say we have a domain like the natural numbers, and we know that for all natural numbers a proposition is true. Does that mean that there exists a natural number such that it is true? In general it does. So if for all x p of x is true, then there exists x such that p of x is true. This is absolutely the case if, as I said, our domain of definition is the natural numbers, or if our domain of definition is really any non-empty set. So the only exception to this is if the domain is empty. Because if the domain were empty, then for all x, p of x could be satisfied trivially without there existing an x to satisfy it. On the other hand, is the converse always true? If there exists x such that p of x, does that mean that for all x, p of x? And of course not. There exists means we can find at least one. But that does not mean that all of them work. So that does not mean for all x, p of x is true. For this last exercise, we're asked for each of the statements below, give a domain of discourse for which the statement is true, and a domain for which the statement is false. So the first statement is, for all x, there exists y such that y squared is equal to x. So what might be a domain of discourse for which this is true? This is true for the domain of discourse is any positive real number. So I'm going to use script R to denote the real numbers, and then the plus sign to mean a positive real number. If we include 0, That's also fine. So why should it be true for the positive real numbers? Well, first of all, y squared is going to be positive for any real number. So I needed to make sure that my x was positive, because if I took all real numbers, then I couldn't say it's true for all x, because the negative numbers, there won't be any number that you can square it and get back a negative number. So we're thinking of y as a square root of x. Then y squared will be equal to x. And we can do this with any positive real number. Find a square root. It also asks us to give a domain for which the statement is false. Like I said, if we included the negative real numbers, it would be false. But also, if we restricted the domain to the rational numbers, it would be false. Even if we took the positive rational numbers, because, for example, 2 is a rational number, so I could let 2 be my x. Remember, I need this to work for all x, so if 2 is my x, then I cannot find a rational number that when I square it gives me 2. The square root of 2 is not a rational number. Okay, what about b? b says for all x and for all y, there exists z such that x is less equal to, z is less equal to y. And we're looking for a domain of definition for which this is true. So I need to be able to always find a z such that for all x, for all y, x is less equal to z is less equal to y. So the first problem that comes into my head is, well, what if x is greater than y? If x is greater than y, then this will fail, and any set that I can take, if it has more than one element, then we could choose x greater than y. So this will be true if the domain of definition is a singleton. So think about singleton 0 maybe. Then if I take x equals 0, y equals 0, and z equals 0, my statement is true because I have these equalities. I can be less than or equal to. So my statement would be true because I would have x equals z equals y. Otherwise, if I had more than one element, say I had 0 and 1, then if I let x equals 1, y equals 0, z equals either one of them, then 1 less equal to 0 less equal to 0 is not true. For C, C says there exists x such that for all y and for all z, y less than or equal to z, if y is less than or equal to z, then y is less than or equal to x is less than or equal to z. And I need to think of a domain of definition so that this could be true. Well, again, I think this will be true if the domain is a singleton. So again, let's take singleton 0, and x is 0, y is 0, z is 0. Then 0 is less equal to 0, so the if part of the hypothesis is true. Then y is less equal to x is less equal to z. This will be true. Then what if I had this at 0, 1? I'm looking for a single x that will work no matter what I pick for y and z. So let's say I pick y equal to 0 and z equal to 0. Then I could pick x equals 0, and this will still work. But then x equals 0 will have to work for all possible choices of y and z. So x equals 0, but what if y is equal to 1 and z is equal to 1? Then I will have y is less equal to z, so the hypothesis of my if-then statement is satisfied, but y less equal to x less equal to z would be 1 is less equal to 0 is less equal to 1. Clearly not true, so this domain of definition will not work either. So that should be the last example for this lecture note and this lesson on logic.